Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the element terbium. I have a sample of it right here in this vial. I hope you can see that. It may be a little hard to see, so I put it on my scanner so you could see it a little bit better. Terbium is a shiny silvery metal when it's kept inside the glass vial away from oxygen. Here we see the beautiful periodic table produced by Theodore Gray. As I've mentioned in previous episodes, Theo has written one of my favorite books called The Elements, which I encourage you to go and pick up. Check out his fantastic website, periodictable.com. Terbium is the 65th element in the periodic table. Its atomic number is 65 because that's how many protons are in its nucleus, and that is what distinguishes it as a unique element. Swedish chemist Carl Gustaf Mosander discovered terbium as a chemical element in 1843. He detected it as an impurity in yttrium oxide. Mosander separated his yttrium oxide, or yttria, into three parts, which he called yttria, erbia, and terbia. There was some confusion because it turned out that his terbia actually contained erbium, and his erbia actually contained terbium. Well, they eventually got things straight. Hey, sometimes science works in strange and wonderful ways. Terbium was discovered from the ore of an obscure mine in the town of Ytterby, Sweden. This small city has 4 elements named after it: yttrium, terbium, erbium, and ytterbium. In addition, 2 other Ytterby rare earth elements, holmium and thulium, are named for Sweden. Holmia is the Latin name for Stockholm, and thulium was named after Thule, the ancient Greek place name associated with Scandinavia. Not bad for a town with a population a bit over 3,500. One commercial source of rare earth elements is the mineral monazite. Monazite is a phosphate with lanthanum, cerium, praseodymium, and neodymium as major substituting elements, and most of the other rare earths as minor constituents. It's usually found in the form of a sand with other minerals. India, Madagascar, and South Africa have large deposits of monazite sands. Another source of rare earths, including terbium, is the mineral bastnasite, which is a carbonate fluoride with lanthanum, cerium, praseodymium, or yttrium as major substituting elements. Both monazite and bastnasite are mined for many rare earth elements. One more rare earth containing mineral has the coolest name, Xenotime. This is normally a yttrium orthophosphate, but other elements can take the place of yttrium, including terbium. Let's take a look at the rare earth content of the previous 3 minerals. You can see from this table, terbium appears in low percentages in these minerals, accounting for only 0.01% of bastnasite, up to 0.26% of monazite, and up to 1% of xenotime. Even though terbium oxides occur in tiny amounts in bastnasite, so much bastnasite is processed for other rare earths, it turns out to be the major source of this element. The only rare earth mining and processing facility in the United States is the Mountain Pass Mine, 53 miles southwest of Las Vegas. The mine supplies almost 15% of the world's rare earth production. While this mine specializes in praseodymium and neodymium, they also extract other rare earths, including terbium, as byproducts. Terbium belongs to a row of elements known as rare earth metals, or lanthanides, since lanthanum is the first element in this periodic table row. Terbium is the 9th element of this series. Technically, both scandium and yttrium are also included in this group since they're both members of the same periodic table column. Both the lanthanide row and the actinide row below it actually fit in the two spaces after barium and radium, but if we displayed the table in this fashion, it becomes too long and unwieldy to fit in books or on posters. As with most elements, the price of terbium varies widely with purity and the quantity you buy. 99% pure terbium goes for about $2,300 per kilogram, a lot more than we've seen recently with the other rare earth elements. The element terbium is uncommon, coming in as the 75th most abundant element in the universe by mass at 500 parts per trillion. At 72nd, terbium is about 1/5 as abundant in the Sun, about 100 parts per trillion. It's the 73rd most abundant element in meteorites, about 39 parts per billion. In the crust of the Earth, it's the 59th most common element, almost 93 parts per billion, more common than iodine, gold, silver, or mercury. Mercury is only 67 parts per billion. Terbium is the 74th most abundant element in the oceans, virtually non-existent at 140 parts per quadrillion. Terbium is over 6.6 million times as abundant in the crust of the Earth than it is in the oceans. And lastly, and not surprisingly, there is no terbium in us. This complicated version of the periodic table shows the evolution of the elements through the history of the universe. Here, you see each element square with a tiny chart of its own, showing that element's growth over the age of the universe by various processes. Terbium is here. I understand this looks complicated, but let's look at just terbium a little closer. The horizontal axis of this square represents time from the Big Bang to now. The vertical axis shows the proportion of terbium created by various processes. The majority of terbium present today is believed to be produced in supernovae, the yellow area. A little less than 1/5 is produced in dying low-mass stars, the magenta area, and a small amount, that green sliver on the top, is produced in neutron star mergers. Note, the terbium produced in dying low-mass stars, the magenta area, doesn't get started until a bit later in the history of the universe. That's because low-mass stars exhaust their nuclear fuel much more slowly and last a long time before they start dying. Each element has many different forms. For each specific element, the number of protons in the nucleus is always the same. 65 protons for terbium, for instance. But there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes. They are chemically identical to each other, but with slightly different weights. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 36 known isotopes of terbium, and of these 36, there's only one stable, naturally occurring isotope, terbium-159. Terbium is therefore a monoisotopic element. More on that in the next slide. Being monoisotopic, the stable terbium-159 isotope obviously makes up all of the naturally occurring terbium in the universe. By the way, the word isotope comes from the Greek, isos meaning same or equal, and topos meaning place, since all these various forms of terbium occupy the same place in the periodic table. There are 21 elements with only one naturally occurring isotope. Of the 21, 2 elements have only one naturally occurring isotope that's also radioactive, bismuth and protactinium. Bismuth-209 may be radioactive, but only slightly so. It has the very long half-life of 2.01 times 10 to the 19th years. That's over 20 quintillion years. Remember that the universe is only 13.7 billion years old. Protactinium-231 has a half-life of 32,760 years. Of the radioactive isotopes of terbium, these 18 are the longest lived, the ones with half-lives over 1 hour. More on half-life in the next slide. The longest terbium half-life, terbium-158, has a half-life of only 180 years. Even the longest terbium half-life is very short, at least in comparison to the age of the universe, which is why none of it exists on the Earth, unless it's made in reactors or atom bomb blasts or as the result of natural radioactive decay. What's a half-life? This graph shows an exponential decreasing curve. As an example, let's say we start with 1,024 atoms of any isotope from the previous slide. You'll see why I chose 1,024 atoms. Hint, it's a power of 2, and we'll be doing a lot of divisions by 2. If you wait one half-life, half of your isotope will decay, and you'll have 512 atoms left. If you wait one more half-life, half of that half decays, leaving you with 1/4 of the original 1,024, or 256 atoms. Another half-life, half again as many, or 128 atoms. And so on. Just keep dividing by 2 every half-life. After 10 half-lives, you'll have about 1/1000th of your original amount. By the way, notice that there's one remaining atom after 10 half-lives. If you waited one more half-life, your remaining atom would have a 50-50 chance of decaying in that time. Terbium has a medium density at 8.2 grams per cubic centimeter. As a reminder, water has a density of 1 gram per cubic centimeter. I've put up some more densities for you here, and you can see that terbium is a bit denser than iron at 7.89 grams per cubic centimeter. Here's a graph of the elements from highest density to lowest density. When I do this talk with an actual audience, I have a set of blocks so you can feel density for yourself, but we'll have to wait to do this until we're back face to face. My set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, and finally magnesium. I also have plastic and wood blocks, but those are not technically elements. Again, terbium's density is 8.2 grams per cubic centimeter, the magenta circle, just above iron. Terbium has a fairly low melting point at 1,356 degrees Celsius, or 2,473 degrees Fahrenheit. It boils at 3,230 degrees Celsius, or 5,846 degrees Fahrenheit, 1,874 degrees Celsius above its melting point. Quite a large difference. If we compare the size of the terbium atom to that of hydrogen, we'd see something like this. The terbium atom is almost 4.4 times the size of hydrogen. Those outer 2 electrons are held fairly loosely. By the way, a picometer is a trillionth of a meter. Atoms are small. Here are atom sizes sorted from largest, cesium on the left, to smallest, helium on the right. Terbium has a pretty big atom, the 12th largest size atom of the elements. All the rare earths are fairly large. I'll mark the other lanthanides in blue. Notice how they're all clustered towards the top of the chart. They all have those loosely held outer 2 electrons. Terbium is a moderately soft element, coming in at 2.33 on Mohs scale of hardness, about the same hardness as your fingernail. Terbium does not expand much when you heat it. It has the 43rd highest rate of thermal expansion, about 10.3 parts per million per degree Celsius. This means that if you had a 1 meter long bar of terbium, we're going to have to magnify this by a factor of 10 just to see it, and you heated the bar by 1 degree Celsius, it would get longer by only 10.3 millionths of a meter, about 1/5 of a hair width. Terbium expands only 4 times as much as the least expansive element, silicon. Here's the periodic table of the spectra. Terbium has a complicated and weak set of emission lines, with very few at the red end of the spectrum. Let's take a look at a few applications of this rare earth element. Some are a bit esoteric, but I'll do my best. Most terbium is used as a fluorescent agent that glows a bright green. Terbium sulfate, a colorless substance under white light, glows brightly under ultraviolet light. Terbium oxide also glows green and is used as a green phosphor in fluorescent lamps and color TV tubes, though picture tubes are now pretty much a thing of the past. We're going to see this glowing application again a bit later. Before we get to the second application, I want to talk about something called the Curie Point. If an object is attracted to a magnet, like this nail, and you heat that object up, it will eventually reach a temperature where its molecules will be moving so chaotically that they will no longer be able to maintain alignment with the local magnetic field. This destroys the object's ability to be magnetized and attracted to a magnet. This is a little over 1,000 degrees Celsius for iron. A standard neodymium magnet, actually made from neodymium, iron, and boron, reaches its Curie point at about 350 degrees Celsius. Adding rare earth elements such as terbium and dysprosium can increase the Curie point and hence the magnet's working temperature by a significant 50 degrees Celsius. The drawback of this method is that terbium is a very expensive additive. Terfenol-D is a unique alloy made of terbium, the ter, iron, Fe is the chemical symbol for iron, and dysprosium, the D, and by the way, the next element in this series. It's about 40% iron with the remaining 60% terbium and dysprosium combined. Why is this alloy unique? I spoke to Dan Bina, CEO of TD Vibe LLC, the only manufacturer of Terfenol-D. When placed in a magnetic field, Terfenol-D changes shape and by a lot, 1 part in 1,000. Let's take a look. Some objects will change their shape when put in a magnetic field. This is called the magnetostrictive effect. If we take a bar of Terfenol-D and put it inside of a coil of wire, this is called a solenoid, when we hook the coil up to a power source, a current flows in the wire, creating a magnetic field inside the coil. The Terfenol-D bar responds by changing shape. The bar can get longer or shorter if we reverse the current. Applying an AC current will cause the bar to oscillate in length. If attached to some mechanism, the bar can apply tremendous force. Soundbug was a speaker device containing a solenoid or coil of wire like we just saw, with a small bar of Terfenol-D. When stuck to a window or a wall and fed an electric signal, the vibrations of the Terfenol-D make the window or wall into an unexpected speaker. As far as I can tell, this device is no longer available, but a British company, Phionic, makes a similar device for commercial applications. Terfenol-D can also be used to make sound waves in water. The powerful pings of sonar are made with Terfenol-D transducers. If there happens to be a submarine beneath our ship, The sound bounces from the submarine's hull, reflecting back to the ship, revealing its presence. Arrays of sonar transducers in a multi-beam sonar can be used to build pictures of the ocean's floor, mapping the topography of the bottom. Some of these are accurate enough to image sunken ships. Adding a terfenol actuator to a lathe tool can allow a machinist to cut with micron or millionth of a meter accuracy. You may have noticed that X-rays have gone digital. You no longer have to wait for the film to get developed. This was first commercially used in 1983. For a chest X-ray, for instance, you stand in front of a panel like this one, and moments later you can see the results on a screen. Terbium is part of a light-emitting phosphor inside the panel that makes this work. Let's see how. We start with a base plate on which we mount a two-dimensional array of photodetectors. On top of these, we place a plate of material that gives off light when hit with X-rays. This plate is called a scintillator. This scintillator is, and stay with me here, terbium-doped gadolinium oxysulfide. The gadolinium helps absorb the X-rays, and as we saw previously, the terbium creates a green glow picked up by the photosensors below. It's pretty efficient stuff, converting up to 20% of the incoming X-rays into light. More efficiency means a smaller dose of X-rays. The photosensors are connected to a computer that reads out the data and constructs a picture. Well, let's see it in action and review the steps. X-rays, after moving through you, hit the scintillator, causing it to glow. This is seen by the photosensor array below. A computer then reads out which of the sensors detected X-rays, and then the computer constructs a picture, which is then analyzed by the radiologist. Your body does not use terbium, but probably still contains a few micrograms absorbed from the environment. There is some hope that terbium may someday provide a more targeted way to treat cancer tumors. As usual, we'll end this talk with Mary Soon Lee's elemental haiku about terbium. Spent kindergarten being teased. TB, TB. Still hate your symbol. In the next program in this series, we'll examine the next lanthanide element, dysprosium. I hope you'll join me. I'm your host, Ron Hipschman. Thank you for watching this Tales from the Periodic Table program about terbium.